So today we're going to start the last section. So we skipped 7.4, we're moving on to 7.5, which is a special type of optimization for multivariable functions. So what we're looking at here is multivariable functions where there's a constraint. All right, we're still going to be finding the optimum value, the maximum or the minimum, but there's a limitation to what we can find. The method we'll be using is the method of Lagrange multipliers. Alright, so remember in 7.3, the last section that we talked about, we found max and minimums of unconstrained. Alright, this would be open-ended, meaning my points could be anywhere. Alright, anywhere on my function, as long as I found a critical value that existed, alright, it works. Alright, so we found unconstrained. So this would be comparing it to what we did with one variable cases. This would be the open case, right? When it's open-ended and our domain can be anything. Right. In this section, we're going to look at cases that are more lifelike, that have limitation or constraints that have been placed on my variable parts. My boundary is no longer open, it's closed. All right. For instance, a fixed budget, right? We can only spend so much money. We can only create so much items because we're limited by time, materials, and things like that. Where this is comparable to is, if you remember, our one variable function case where we were limited on the domain, right? When we said our domain exists between point A and point B. The closed case, right? Where we solved using the extreme value theorem. Something similar is going on here. It's a little more complex, but it's a similar type idea. So it's comparable, right? This is sort of the same idea. So remember, if we had a closed case, and we want to find the max and min, the extreme value theorem stated, we had to take into account not just any critical values, but also the end points, right? Our max and mins could be at the end points, all right? Where that's going to be comparable to a multivariable function is we have to take into account the constraint. All right, so for a multivariable function, right, the same thing's going to be true. The algebra is just a little more difficult. So we set up a process. It's going to be more of a process that we're going to go to. Instead of having a closed domain, what we have instead is we are going to be restricted to what's called the constraint equation. All right, so a constraint equation, which I'm denoting g of xy. All right, so our xy values have to be equal to some k. So k would be our limiting value. The k would represent our budget, our time, all right, whatever it is that's limiting us. And so our constraint equation would be involved in some way too. So g of xy is equal to k, or more correctly, it would be less than or equal. So k would represent a budget, right? And so I can spend up to k, but technically I could spend less than k if I wanted to. And so it is more proper to say less than or equal to k, although when we set it up, we usually do the equal to k's just to make it simpler. Although we will look at an example where the less than or equal to will come into play. So again, it is less than or equal to our constraints. So again, same thing, time, right? If we only have 100 hours to spend, well, I can spend up to 100 hours creating my object, or I could spend less than it if I'm a little more efficient, but I can't go over 100 hours, right? I'm less than or equal to the constraint. All right, so this would be our limiting factor, which means when we find our critical values of f of x, right, they have to also make the constraint equation true. All right, my x and y values have to be critical points that exist in my limitation, in my constraint equation. All right, so again, limited value, or critical values, or max and mins, are limited to critical points that make the constraint equation true. So that's the big part of this. Again, it's like the one variable case. We can only find critical values within the limited domain. Well, we can only find critical values within the constraint. All right, because this involves two or more variables, it's a little more complex, and so there are different methods that were created to solve this. All right, I'm using the method of the Lagrange multiplier and the Lagrange function to solve these types of applications with constraint. I am going to make a note here that my method is different. All right, the way it's set up in the algebra that we do is different than the book, ergo different than what's on Connect, right? Because Connect is basically the online book material. So just make sure you're aware of, now, it's actually solving the same way, it's just a different way to solve it. The book uses more of an algebraic method where you solve it and then you solve the system algebraically. I use a method where I do set up algebraic equation, a system, but I set it up in a way where I can use a matrix. I can plug it into technology and solve it for me. All right, so that's why that's why I prefer my method. Although, like I said, both methods are perfectly valid. Both methods are good. Actually, sometimes the book's method's a little easier if it's not a case where I can use a matrix. But 90% of our cases will be. So I'm going to stick to using my method. But just so you're aware of that, the book, again, does do something a little differently than I do. All right, what I use is I use a method of Lagrange using an optimization function. All right, so first one, I have to set up that function, that formulation. All right, so the problem will give us an original function we want to optimize, like profit, cost, revenue. We want to maximize, minimize. It'll also give us a constraint equation. Either the problem will state what the constraint equation is, or there'll be some description where I'll write it down. When we get to applications, sometimes we have to find this, but usually it's pretty straightforward. I only have so many hours I can spend, or my budget's a certain amount, and again, they'll be pretty straightforward and linear cases. Then we go to set them up. Now, I did write the equal to case. All right, although technically speaking, it would also be true for the less than or equal to k. But just to make life simpler, I dropped the less than. I'm just setting it up as the equal to, but the less than is also implied in there. The first thing I do to set up my constraint equation, I set it equal to 0, right? Because that's actually the part we're going to use. So what that consists of, usually there's some constant here that represents a budget amount or something. I subtract that and move it to the other side and set it equal to 0, because this is the expression I'm going to be using in my formulation. All right, and so I'm going to create what's called the Lagrange function or auxiliary function, where I'm going to introduce the Lagrange variable. All right, lambda, all right, this Greek letter lambda here, is the Lagrange multiplier. All right, it's a check. It does have meaning in economics. Again, we don't do anything with it in this class. We're just going to find it. We're more interested in the x and y values that are going to optimize our original function f of x. So again, we'll find it. It does have meaning, and the book talks about it a little bit, but we're not going to do anything with it. We're just interested in setting it up and finding our point, x and y values, that give us our optimum value. All right, give us what we're looking for. All right, so the function that we get, the Lagrange auxiliary function, is this capital F of x, capital F of x, y, and the new variable lambda. And there are two expressions that are involved. There's the f of x, so the f, I'm going to write over here, the f of x, y, that's the original. All right, whatever it is we were originally interested in. So this would represent profit function, cost function, revenue function, whatever it is we were originally given in the application that we want to optimize. Then what we do is we introduce a second part of this that takes into account the constraint. This is where the Lagrange multiplier is going to come a part of. It's the Lagrange multiplier times, if you look there, times the constraint equation where I've set it equal to 0, right? That was that expression I had up here. The constraint equation where I've set it equal to 0, right? This piece here is that part of this auxiliary function. All right, so lambda times that expression. All right. Now we have three derivatives that we're going to find. We have three variables. We have the x variable, the y variable, and then the new Lagrange variable. But again, it seems complex, but they're actually fairly straightforward. All right. They're basically the same setup every time. What you do is when I want to find the derivative with respect to x, remember there's two parts to this, I find the derivative of the original function, right? This would be the original function with respect to the variable I'm looking at. And so the derivative of the lowercase f of x with respect to x. So I take this derivative with respect to x. Then I add to it lambda times the derivative of the constraint, which has the x value in it. And so lambda, remember, is a constant multiply. It'd be like if it was 10 times that. Lambda's going to always come along, and it's times the derivative of the constraint, the g function, with respect to x. And that's always what it is. The derivative of the original with respect to x plus lambda times the derivative of the constraint with respect to x. Same thing for y. I take the derivative of the y part, so I take the derivative of the original function, which is the lowercase f with respect to y, add to it, lambda is just a constant multiplier, comes along, times the derivative of the constraint, the g function, with respect to y. Alright, and that's the derivative with respect to y. Alright, and then what always happens with the derivative with respect to lambda, it's always the same thing. If you look at this, this is the only variable that's lambda in the whole entire expression. And so when I take the derivative with respect to lambda, right, that's the variable I'm looking at. So if there's no lambda, it's considered a constant and zeroes out. So the original function has no lambda in it. And so that will zero away, all right? And so this is the only part I look at. Well, lambda's the variable part. The g of xy minus a constant, is multiplying times lambda. Well, that g function is just a constant, right, times my lambda variable. And so the derivative of just lambda is 1 times the constraint equation, because that's considered a constant multiplier. Right, it's just the same as when we had the xy variable, you know, when I took the derivative of x times y with respect to x. Well, the derivative of x was 1 times y, because y is considered a constant. Same thing, this time the y part's just a little more complex. But what you just have to remember is the derivative with respect to lambda is always the constraint equation where I've set it equal to 0. Right? Because 1 times that is just the, and that's always what it is. Alright? It's always the constraint equation, exactly the way it was when I set it equal to 0. And actually, that's my next step. So it actually is the whole entire thing where I set it equal to 0, right? Step 3 is set all of them to 0 and show this. So set all 3 of them to 0. Because in order for my next step to be true, right, I want to find my critical values. My critical values only exist where my function equals 0, and so we set them all equal to 0. Alright, so those are all candidates for the extreme value theorem, taking into consideration the constraint, because the constraint is involved, and so is my original function, right, in the whole entire process. Alright, and so those are the functions, the system of equations that we'll be using. Alright, and so then we solve. And so if they're linear, and most of our cases are linear, the linear functions would be meaning I can rewrite my original equations where it's an x times a number plus b times a y value, so b would be my number, and some number times lambda where it equals a constant. The constant could be 0, right? So again, 0 is a constant, or it might be some constant I have to move over and set it equal to that constant value. Again, 90% of our cases will be theirs. If it's not that case, we do have to solve by substitution, and like I said, I'll do one example of that case, but 90% of our outcomes are the linear cases where we can throw them into a matrix. And so those are the ones we're going to be practicing for the most part. Alright, once you've solved, again, most of ours will be solved with a matrix. Then the critical values that you found are critical values that are within my constraint. And if there's more than one, alright, we plug those values back in the original. The biggest number that comes out is my maximum. The smallest number comes out is my minimum, just like the extreme value theorem for the one variable case. If you only get one, and most of ours will, when it's the linear case, it's the one critical value case, we assume it's the one we're looking for. Alright, so if we're looking for maximum, the critical value is finding the maximum. If we're looking for minimum, the critical value is finding our minimum. Alright, so there's the process. And now I'm going to walk through one example of that process, and then we'll get into the applications, but that'll be the next set of notes. Alright, so the first example, just kind of walk you through it in a simple case. So my original function, f of xy, is that 5x squared plus 6y squared minus x times y. Assumes a relative minimum subject to the constraint. And so there is my g of xy, and my constraint k is 24. And so the first thing I'm going to do is rewrite that where I'm setting equal to 0. So I'm subtracting 24, so I get x plus 2y minus 24 equals 0, because this is the piece that I'm going to put into my Lagrange function. Alright, so here's the Lagrange function I'm going to plug my parts into. So my capital F of x represents the Lagrange. The first thing I write down is the original function. And then plus the new variable lambda times that expression, my constraint equation that I've set equal to 0. So the x plus 2y minus 24. And again, it's in parentheses, as that entire expression is being multiplied by my Lagrange variable, my lambda. Alright, now I find my three partial derivatives. Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to lambda. But remember, it's the same thing every time. And I forgot my square on my y term. Alright, make sure I write it down. Alright, 5x squared, 6y squared minus xy. Alright, the first step is I take the derivative of the original, right? This is the piece of the original, f sub x. Then I'll add to it lambda times the derivative of the constraint with respect to x, right? Because I'm looking at the x direction. Alright, so the derivative of the first piece with respect to x, well, there's two x terms, so I get 10x minus y, right? The derivative of the f sub x is 10x minus y, plus lambda times the derivative of the constraint with respect to x. Well, again, I'm looking here. There's just this 1x value. The derivative of just x is 1. All right, so it's going to be lambda times 1. Go ahead, set it equal to 0 so you don't forget. That's stated in my next step, but I just say good rule of thumb, just go ahead and do it right away so you don't forget. All right, now I do the exact same thing with respect to y. All right, so now instead of sub x, I'm looking for sub y. So I take the derivative of the original with respect to y plus lambda times the derivative of the constraint with respect to y. Alright, so there's two y parts in the original. There's the 6y squared, which will give me out 12y. And then there's the negative x times y, so negative x. Plus then the lambda times the derivative. So again, I'm looking here, taking the derivative of my g of xy. Again, there's only one y term, the 2y. Derivative of 2y is 2. Alright, so it's going to be lambda times 2, and then go ahead and set it equal to 0 so you don't forget. The last function, or the last partial derivative, is the derivative with respect to lambda. Right? There's only one lambda part. Right? If I look at this, that's the only lambda variable. There's no lambda variable in the original function, so those are all considered constants. They zero out. It's lambda times this expression, which there's no lambda in, so those are all considered constants. So it'd be like lambda times 10. The 10 would come along, the derivative of lambda is 1. Well, the derivative of lambda is 1. The constant's just a little more complex. It's the constraint equation. It's always the constraint equation. It's 1 times the constraint set equal to 0. Right? And again, that's always the constraint set equal to 0 because of how we set up the equation. Alright, and so there are my three partial derivatives. I've already done this part. Set the partials equal to 0. Always show this because in order to solve the system, I can only solve it if I've set it equal to 0. Alright, key step, make sure you show it. Alright, this is a linear case, meaning I can solve with a matrix. Alright, I can put them in the form ax plus by plus c lambda equals some constant. In this case, the constant for the first couple of ones will just be 0. Alright, so the first equation is actually set up. It's good to go. Alright, it's got x, y, lambda equals 0. So it's 10x plus, not plus, negative 1y plus 1 lambda equals the constant 0. Alright, the second equation, the constant 0, but I do have to reorder my y and my x, right? X first, so negative x first, then positive 12y, and then 2 lambda, all right, equals my constant 0 in that case, all right? So make sure you write them in the right order, because when I go to plug them in my matrix, x first, y second, lambda third equals my constant. In this case, it's just 0. My last equation, I do have a constant 24, so I do need to move that to the other side. So I'm going to add 24 and move it to the other side. There's no lambda, so I'm going to leave that part kind of blank. So it's just my x term, which is just x, plus my y term, which is 2y, space, there's no lambda, equals my constant that I moved over, which is 24, which there's my original constraint. That last line is always gonna be the original constraint. Alright, so now I've set up my system of equations correctly. Now I can solve with the matrix. And so I plug them into my matrix form. And so you go to your matrix key on your calculator. It's going to be a 3x4. It's a little bigger. I've got 3 equations, 4 columns, right? 1, 2, 3. Then there's the column for x, column for y, column for lambda, column for my constant. And so make sure you make it big enough. It's a 3x4. The first row is my first equation. So 10, -1, +1, 0 is my first row. Second row, -1, +12, +2, 0. The last row, 1, 2, there's no lambda, and so we put a placeholder 0 there, right? And then 24, all right? There is the equation that you want to make sure you plug into your matrix. And then row reduce. All right, again, this is the work you want to show. All right, so when you row reduce, it should come out the simplified form, which means diagonal zeros, diagonal of 1, zeros everywhere else, and then the number. So plug it in, make sure you go RREF, and then it should give you 6, 9, -51. And so remember, the first line is your x values, right? This is x, y, lambda, constant. So the first line's giving me x equals 6. The second line's giving me the y equals 9. And the last line's giving me my lambda variable equals -51. Which again, we found the lambda. We're not going to do anything with it. Our solution's only going to involve our x and y. Alright, so our critical value that lands within our constraint is 6 for x, y is 9. Alright, and so again, there's only one, so it's assuming what we're looking for. So I'm going to go back up here and remind myself what I'm looking for. Alright, so our critical value is our relative minimum, which I found the location, right, that's the critical value. And now I need to find the minimum, so I've got to plug it into my original equation. And I'm going to write that down here in that step. Alright, so, oops, too far. Alright, so we found the location of the relative minimum. Is the 0.69. The relative minimum is, well, I've got to plug the 6 and the 9 into my original equation. F of 6, 9. So again, I'm going to write it down here. So it's 5 times 6 squared plus 6 times 9 squared minus 5 times, not minus 5, minus 6 times 9. And when you plug that into the calculator, it should come out 612. Alright, so my minimum value for this function, my relative minimum value is 600, whatever it means, cost, revenue, profit, whatever it means. The minimum is found when x is 6, y is 9 within my constraint, so it still lands in my constraint, and the value is 612. And so that's sort of that's the setup for the Lagrange that we're going to be using. Just a quick note, the next problem, I'm going to skip problem number 2 from the notes. Alright, again, we lost a week of school by extending spring break. This is one of the places where I'm going to sort of kind of give it back. We're not going to do anything like number 2, so it would be a substitution case, which the algebra is a little harder, and so I'm going to omit it. We'll be doing a case in the applications that's a little simpler than this one. This one's more complex than anything I'm going to ask. So skip problem number 2. We're going to head on to applications. Alright, in the applications I will do one example where we have to solve by substitution, but it's a lot easier case than number 2. The algebra number 2 is a little trickier, and so I'm going to use this opportunity to skip that. Alright, so we're going to skip that, and in the next set of notes we're going to start applications of optimization using the Lagrange multiplier, and that is where the next video will pick up. Alright, we'll stop there.